The Industrial Revolution, 1750 to 1900, dramatically transformed life and work in Europe and the United States. During this time, inventors and their creations led the way in shaping a new society. The invention of these ingenious machines enabled the mass production of high-quality cotton and woolen thread and yarn, helping to transform Great Britain into the world's leading textile manufacturer in the second half of the 18th century. Around 1764, James Hargreaves, a poor and uneducated spinner and weaver from Lancashire, England, invented a new type of spinning machine that could draw thread from 8 spindles simultaneously, unlike the traditional spinning wheel that only used one. The idea reportedly came to him when his daughter Jenny accidentally knocked over the family's spinning wheel, and he noticed the spindle kept turning even as the machine lay on the floor. This inspired Hargreaves to create the spinning jenny, and he obtained a patent for it in 1770. The water frame, patented in 1769 by Richard Arkwright, was powered by a water wheel and became the first fully automatic and continuously operating spinning machine. It produced stronger and larger quantities of thread than the spinning jenny. Due to its size and power source, the water frame couldn't be used in homes like earlier machines. Instead, it required a large building near a fast-running stream. Arkwright and his partners built several factories in Britain's mountainous regions, where spinners, including child laborers, worked in increasingly large factories rather than at home. In 1779, Samuel Crompton invented the spinning mule, combining features of the spinning jenny and the water frame. His machine could produce both fine and coarse yarn and allowed a single operator to manage over 1,000 spindles at once. However, Crompton was poor and couldn't afford to patent his invention. He was cheated by a group of manufacturers who paid him far less than promised for the design. Despite this, the spinning mule became widely used in hundreds of factories across the British textile industry. The steam engine, used in manufacturing and as a power source for ships and railway locomotives, significantly increased factory productivity and contributed to the vast expansion of transportation networks both nationally and internationally during the 19th century. In Britain in the 17th century, primitive steam engines were used to pump water out of mines. In 1765, Scottish inventor James Watt, building on earlier improvements, increased the efficiency of steam pumping engines by adding a separate condenser, and in 1781 he designed a machine to rotate a shaft rather than generate the up and down motion of a pump. With further improvements in the 1780s, Watt's engine became a primary power source in paper mills, flour mills, cotton mills, iron mills, distilleries, canals, and waterworks, making Watt a wealthy man. British engineer Richard Trevithick is credited with inventing the steam railway locomotive in 1803, a use of the steam engine that James Watt had once dismissed as impractical. Trevithick also adapted his engine for use in barges and dredgers, and it generated more power than Watt's design by operating at higher pressures. His engine soon replaced Watt's less efficient design in industrial applications in Britain. The first steam-powered locomotive to carry paying passengers was the Active, later renamed Locomotion, designed by George Stephenson, which made its first run in 1825. In 1830, Stephenson and his son designed the rocket for a new passenger railroad line between Liverpool and Manchester, achieving a speed of 58 kilometers per hour. In the late 19th century, two key inventions improved the safety and efficiency of steam trains. In 1897, American inventor Andrew J. Beard patented the Jenny coupler, which automatically connected railway cars, eliminating the dangerous task of manual coupling. Around the same time, Canadian-American inventor Elijah McCoy patented the McCoy lubricator, a portable device that automatically lubricated steam engine bearings while the train was in motion, allowing continuous operation without frequent stops for oiling. Steamboats and steamships emerged in France, Britain, and the United States during the late 18th and early 19th centuries. The first commercially successful paddle steamer, the North River Steamboat, designed by American engineer Robert Fulton, traveled the Hudson River from New York City to Albany in 1807 at about 8 kilometers per hour. Larger steamboats later transported passengers and cargo along the extensive inland waterways of the eastern and central U.S., particularly the Mississippi River. The first transoceanic voyage using steam power was completed in 1819 by the Savannah, an American sailing ship with an auxiliary steam-powered paddle. It traveled from Savannah, Georgia, to Liverpool, England, in just over 27 days, with the paddle operating for 85 hours of the trip. By the late 19th century, increasingly large and fast steamships, known as the Atlantic Ferry, were regularly transporting passengers, cargo, and mail across the North Atlantic. In the early 19th century, scientists in Europe and the United States studied the connection between electricity and magnetism, paving the way for practical uses of electromagnetic phenomena. In the 1820s and 30s, British scientist Michael Faraday demonstrated two key principles of electromagnetism. He showed that passing an electric current through a coil of wire between two magnet poles would cause the coil to turn, forming the basis of the electric motor, which converts electrical energy into mechanical energy. He also discovered that turning a coil of wire between two magnet poles would generate an electric current, laying the foundation for the electric generator, or dynamo, which converts mechanical energy into electrical energy. While motors and generators improved significantly in the mid-19th century, their widespread use relied on later innovations, such as electrically powered trains and electric lighting. German engineer Werner von Siemens demonstrated the first electric railway for urban mass transit in Berlin in 1879. By the early 20th century, electric railways were running in and between major cities in Europe and the United States. London's subway system, the London Underground, introduced its first electrified section in 1890. In 1878–79, Joseph Swan in England and Thomas Edison in the United States independently developed practical electric incandescent lamps, which produce light by heating a filament with an electric current in a vacuum or near vacuum. Both inventors filed patents, and their disputes were resolved in 1883 when they formed a joint company. Edison is often credited with the invention, as he also created the power lines and equipment needed for a practical lighting system. Over the next 50 years, electric incandescent lamps gradually replaced gas and kerosene lamps as the primary source of artificial light in urban areas, although gaslit street lamps remained in use in Britain until the mid-20th century. In 1881, American inventor Lewis Latimer patented a carbon filament that significantly extended the life of light bulbs compared to earlier designs. This innovation made light bulbs more efficient and affordable, helping to accelerate the widespread adoption of electric lighting. The 19th century saw the invention of the electric telegraph and the telephone, which enabled reliable, instant communication over long distances for the first time. These innovations had an immediate and lasting impact on commerce, diplomacy, military operations, journalism, and everyday life. The first practical electric telegraph systems were developed in 1837, almost simultaneously in Britain and the United States. British inventors William Fothergill Cooke and Charles Wheatstone created a system where needles on a receiver pointed to letters or numbers when electric current passed through wires. Meanwhile, in the United States, inventors Solomon Brown, Joseph Henry, Samuel Morse, and Alfred Vail contributed to their own telegraph system. Brown served as a principal technician. Henry designed the high-intensity magnet. Morse conceived the telegraph's design, and Vail made significant improvements. Morse also developed Morse code, a universal system of dots, dashes, and spaces, which became a global standard for telegraphy. A demonstration line between Washington, D.C. and Baltimore, Maryland, was completed in 1844, with the first message reading, "What hath God wrought?" Telegraph cables were laid under the English Channel in 1851 and across the Atlantic Ocean in 1858. In the United States, the expansion of telegraph systems, led by companies like Western Union, supported law and order in Western territories, regulated railroad traffic, and facilitated national and international news via wire services like the Associated Press. In 1896, Italian physicist Guglielmo Marconi advanced wireless telegraphy, which became crucial for military applications in the 20th century. In 1876, Scottish-born American scientist Alexander Graham Bell demonstrated the first successful telephone, capable of transmitting sound, including the human voice, via electric current. Bell's invention used two sets of metallic reeds and electromagnetic coils. Sound waves near one membrane caused it to vibrate, generating electric currents in the attached electromagnetic coil. These currents traveled to a second coil, causing its connected membrane to vibrate and reproduce the original sound. Bell's historic first call took place on March 10, 1876, in his Boston laboratory, where he famously summoned his assistant, Thomas Watson, with the words, "Mr. Watson, come here, I want to see you." While Bell is credited as the primary inventor of the telephone, American inventor Lewis Latimer played a crucial role in its development by creating high-quality patent drawings for Bell's application. Initially viewed as a luxury for the wealthy, the telephone became a widely used household device by the mid-20th century, with billions in use worldwide. Among the most consequential inventions of the late Industrial Revolution were the internal combustion engine and, along with it, the gasoline-powered automobile. The automobile, which replaced the horse and carriage in Europe and the United States, offered greater freedom of travel for ordinary people, facilitated commercial links between urban and rural areas, influenced urban planning and the growth of large cities, and contributed to severe air pollution problems in urban areas. The internal combustion engine works by burning a compressed mixture of air, oxidizer, and fuel inside the engine, with the resulting hot gases driving components like pistons or rotors. The first commercially successful engine of this type, powered by coal gas and air, was built in 1859 by Belgian inventor Etienne Lenoir. Although initially inefficient and costly, the engine was significantly improved in 1878 by German engineer Nikolaus Otto, who developed the four-stroke cycle, induction, compression, firing, and exhaust. This design became the foundation for modern gas-powered engines, which soon replaced steam engines in smaller industrial applications due to their efficiency and ease of use.
In 1885, German engineer Gottlieb Daimler created the first gasoline-powered internal combustion engine, also based on Otto's design.
A few years later,
Rudolf Diesel developed a more efficient internal combustion engine that ran on heavy oil instead of gasoline.
The diesel engine became widely used for powering locomotives, heavy machinery, and submarines.
The gasoline-powered engine, with its efficiency and light weight, was ideal for light vehicles. In 1885, Daimler built the first motorcycle powered by an internal combustion engine,
while Carl Benz constructed the first motor car. By the 1890s, automobile production began in Europe and the United States,
catering mainly to wealthy customers. Less than 2 decades later,
American industrialist Henry Ford revolutionized the industry by perfecting assembly line manufacturing. His methods enabled the mass production of affordable vehicles, such as the Model T, making automobile ownership attainable for average-income Americans,
a transformative moment in transportation history.
Advances in farm machinery, along with chemical and agronomic innovations,
transformed agriculture into a high-yield industrial enterprise during the Industrial Revolution.
These developments significantly increased food production, helping to sustain the rapidly growing population.
In 1837,
John Deere revolutionized farming with the invention of the steel plow, which was lighter, stronger, and more efficient than earlier iron and wooden versions. Its sharp point and smooth surface reduced friction, making it easier to break up the dense prairie soil of the American Midwest. This innovation allowed farmers to cultivate more land with less effort,
boosting crop yields and facilitating westward agricultural expansion.
By the 1850s, Deere's company was producing over 10,000 steel plows annually, transforming U.S. farming.
In 1831,
Cyrus McCormick introduced the mechanical reaper, a groundbreaking invention that revolutionized grain harvesting. This horse-drawn machine featured a cutting bar to slice ripe grain, a platform to collect the cut stems, and a reel to guide them onto the platform for bundling. By automating the cutting and threshing processes,
the reaper drastically increased efficiency,
allowing farmers to harvest 4 times more grain per day compared to traditional handheld scythes, which had been in use for over 5,000 years.
Norbert Rielau,
a chemist and inventor, transformed the sugar industry with his invention of the multiple effect evaporator,
patented in 1846.
This innovative device used steam heat and vacuum chambers to boil sugar cane juice in stages, efficiently removing water while preserving sugar crystals. Compared to the traditional open kettle methods, Rieau's apparatus significantly reduced fuel consumption, increased sugar yields, and improved production quality,
lowering costs and boosting profits for Louisiana sugar plantations.
His groundbreaking contributions to industrial heat transfer and steam technology paved the way for advancements in chemical processing, pharmaceutical manufacturing, food and beverage production, and wastewater treatment, with his refining process still in use today.
George Washington Carver, an American agronomist and inventor,
is renowned for promoting sustainable farming practices, particularly crop rotation, to rejuvenate soil depleted by cotton monoculture. By advocating for nitrogen-fixing plants such as peanuts, soybeans, and sweet potatoes,
Carver helped restore soil fertility while diversifying agricultural outputs.
Through his innovative research in synthetic production,
he developed hundreds of practical applications for these crops.
For peanuts alone, he created over 300 products, including substitutes for milk and oil, as well as materials like paper and wood stains. Carver's work provided affordable solutions for impoverished farmers and significantly reduced Southern agriculture's dependency on cotton, fostering economic resilience in the region. Mass production and expanded distribution made consumer goods like clothing and cosmetics affordable and accessible to everyone. In the 1840s and 1850s, Elias Howe and Isaac Singer patented sewing machines. Howe created the first practical sewing machine using lock stitching, which could produce 300 stitches per minute, far faster than the 40 to 50 stitches a seamstress could make. However, it could only sew in a straight line. As technology improved, garment factories could mass-produce affordable clothing for the public. The sewing machine later became a common household item, promoting self-reliance. In 1851, Singer developed an improved model using Howe's lock-stitch method and a new motion mechanism. After a lengthy legal battle, Howe regained his patent rights in 1854 and received royalties from all U.S.-made sewing machines. In 1883, American inventor Jan Ernst Matzeliger created the shoelasting machine, revolutionizing shoe production. Before this, shoes were individually crafted by skilled artisans, limiting their availability and cost. Matzeliger's machine could produce 150 to 700 pairs of shoes per day, compared to just 50 per artisan, making affordable, mass-produced shoes widely available. In 1856, English chemist William Henry Perkin patented aniline dyes, enabling the mass production of vibrantly colored fabrics. Before this, dyes were made from natural sources and had limited color options. Perkin accidentally created aniline purple, or mauve, while trying to synthesize quinine, a drug. This new dye process made brightly colored, affordable clothing accessible to the masses. The popularity of mauve was so widespread it was called Mauvain measles and even caught the attention of the British royal family. Queen Victoria wore a mauve silk dress at the 1862 International Exhibition, also known as the Great London Exhibition. In the early 1900s, Madam C.J. Walker, born Sarah Breedlove, created a line of cosmetics and hair products for African American women, focusing on pomades and shampoos. Through clever marketing and by training a network of over 25,000 sales agents, she built a business empire that extended from the United States to Central America and the Caribbean. Walker's success helped transform cosmetics from small-scale production to mass-market consumer goods. Thanks for watching. The Industrial Revolution, 1750 to 1900, dramatically transformed life and work in Europe and the United States, with inventors and their innovations leading the way to a new society. Don't forget to like, comment, and subscribe for more insights into history's game changers. See you in the next video.